The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's webinar. It's titled Attacks on Games and How to Defend Them from Hacker Threats, Game Security Best Practices and Case Examples. My name is Jody Wadwa. I'm the VP of Marketing here at ArcSen, and I'll be moderating today's webcast. We have two security experts in gaming with us today that will share their perspectives on game security. Our first presenter will be Amit Sethi, Technical Manager at Cigital, and I'd also like to welcome Rennie Allen, Security Solutions Architect at ArcSen. Before I hand it over to Amit, I'd like to go over a couple of logistics. We welcome any questions for the webinar, and please use your chat utility at the bottom of your dialog window that you see there. All questions will be answered at the end of the webinar. At this point, I'd like to welcome Amit to begin our webcast. Amit?
Okay, thank you. Rennie, if you could transition to the next slide. So, today's agenda, first we're going to talk about what is an online game. What is it about games that makes it so different? Then we're going to talk about some common hacks. Now, these are examples of complete and interesting attacks that attackers often carry out against games. Then we're going to talk about common attack vectors and mitigation. These are the low-level techniques that attackers use to carry out the attacks that we discussed in the previous section. Then we're going to talk about game security with client-side hardening. That is, what client-side techniques we can use to prevent the attacks that we discussed. Finally, we're going to talk about securing overall game design. Next. So what is so different about video games? When it comes to offline games or online games that require no real-time interaction between players, there really isn't anything all that different. But when it comes to online games that do require real-time interaction between players, things get very interesting. Now, you may already know that for most websites, a round trip to the server of less than 200 to 400 milliseconds is typically considered good. Now, for online games, a round trip to the server of less than about 100 milliseconds is considered good. Now, let's think about that for a second. Even if the server had the ability to do all computations instantaneously, and the client had the ability to render the server's responses instantaneously, we would get a new state for the client to render about once every 100 milliseconds. Now that translates to about 10 frames per second. Now can you imagine playing a first-person shooter or a baseball or a soccer game at 10 frames per second where the server is making all the decisions? That's not going to be a lot of fun. So in reality, what we really need to aim for is about an 8 millisecond to 16 millisecond response time for the user to ensure that they don't notice any kind of lag. Now this is the amount of time from the moment they actually press a button to the moment they see the resulting action on the screen. So what kind of bandwidth, latency, and computational requirements do you think are needed to achieve that if we're doing everything on the server side? Well, whatever is required, we don't have it yet. We'll probably eventually get there, but not anytime in the near future. Next. So let's take a look at what a typical online applications architecture looks like. We have a bunch of clients talking to a server, which in turn talks to some back-end web services and databases. Now, what are some of the assumptions that we typically make in this architecture? First, we assume that the user can see everything that is sent to the client. So if you want to keep something secret from the user, you don't send it to the client. Second, we assume that users can manipulate everything that is sent to the server. Next. With online games, the architecture starts looking a lot more distributed. Let's take a look at the picture on the right. We have a lot more servers doing many different things. For example, in World of Warcraft, different servers handle different parts of the online world. In first-person shooter games, different servers host different games. In most cases, these servers need to talk to each other, at least once in a while. Now let's take a look at the picture on the left. A subset of all the players' state is stored on the server side. Note that it's just a subset. The server doesn't need to know every little detail about every single player. The client side, however, has a complete picture of your state, as well as the state for players that you're currently interacting with. So if another player is hiding behind a wall right in front of you, the game client knows that. The client is making the decision about whether the other player is visible or not. Having the server make that decision is way too difficult, and remember, we talked about the issue with lag. So we have state maintained by the game client that you as the player are not supposed to know. Now this is very different than the general case where we assume that the user knows everything that is being sent to the client. Okay, next, and I'm going to pass it over to Rennie at this point. So we're going to skip over this slide.
Okay, thanks, Amit. So basically, within gaming, we have a series of risks. Typically, for single-user games, the risk is piracy. It's just simply enabling the use of the game where it might be a licensed game. Once we move into multi-user games, cheating becomes an issue. Cheating is generally not an issue in single-user games because nobody really cares if somebody cheats themselves. But in multi-user games, cheating basically impacts other users and affects their experience in the game. The other thing that can happen, and again, it's a revenue, it's very similar to piracy, would be ad removal if you have a mobile game that is ad generated. Hackers can basically put a hack in to remove the ads. There's also potential for paywall bypass, although I haven't seen that too often. And basically unauthorized game servers is another use case. Basically, somebody providing a server and hosting games that's unauthorized and not part of the legitimate game environment. And then there's just all sorts of general client compromise. All of these can result in revenue loss. Basically cheating, destroying the value of the game can destroy your entire game base, which is your entire revenue stream. So what are the common hacks that are often seen in multi-user games, online games? Aimbots and trigger bots are very common in first-person shooters. So basically, the way these work is there's either some internal code that gets injected into the game client, or there's an external machine that tracks objects within the game and automatically aims the player's weapon or automatically triggers the player's weapon when they are aimed at a target. So essentially, it makes the play very unfair for other players who are not using such a device. The other common hack for multi-user games is radar hacks. This is where the user can see outside of the fog of war. So basically, where they're allowed to see in the normal gameplay, they can see beyond that through radars, which are either top down, allows them to see everything throughout the field of view, or allows them to potentially see targets mapped behind, in the regular 3D first-person view, to see targets mapped behind them. The other thing is texture hacks, where basically you simply change the textures that are mapped onto objects such that they're transparent. So of course the other players on their game clients, they have the regular textures, they can't see you, and you have the clear transparent textures and you can see the players behind them. So the common attack vectors. For this, I will hand it back over to Amit.
Thanks, Rennie. Let's go to the next slide. So popular games out there contain a lot of source code. For example, World of Warcraft contains 5.5 million lines of code. That includes both the client-side and the server-side code. Now, if there's one thing that history has taught us, is that more code results in more bugs, which in turn results in more security issues. Now, to make matters worse, what language are games typically implemented in? Typically unsafe languages like C and C++ for performance reasons. So all of those nasty vulnerabilities, like buffer overflows, are often found in games. Even simple techniques like random fuzzing can often be used to find remotely exploitable or locally exploitable vulnerabilities. Now, an attacker's goal when exploiting these types of issues is often not some kind of game hacking or cheating, like some of the examples that we just saw. It's generally to gain complete control over the game client or the host machine or the console. So how do we prevent these types of problems from popping up? We have to use security touchpoints in our software development lifecycle, especially when it comes to code reviews and security testing. Next. Now, time and state management issues. This is one of the most common types of issues that we see out there in online games. And exploiting these issues often doesn't require any real hacking or security knowledge. And we're going to see a couple of examples of these on subsequent slides. Now remember that online games often require a significant amount of state to be pushed to the game client. Of course, the bandwidth that users have available varies significantly, and massively multiplayer online games contain virtual worlds that are split across hundreds or thousands of servers. Now, if you're trying to maintain a consistent state in a situation like this, where you have overlapping states distributed across many systems, both client and server, that are all communicating with each other at varying speeds, the problem becomes very difficult. Next. So one example of a time and state management issue is artificial lag. Now, this is one way in which players try to exploit time and state management issues. The game client typically does have enough state so that it can continue playing the game for a couple of seconds, even if it doesn't get any data from the server. Now, what exactly does that mean if I'm not getting any updates from the server? Well, I have complete control over my character in the game client, regardless of what's coming down from the server. Now, other players only have control over their characters in my game client as long as network traffic from the server is getting to my game client. So if I can slow down or stop traffic from the game server, the other players lose control over their characters in my game client. Now, that gives me an unfair advantage. Now, when my game client sends an updated state to the server based on gameplay where I had an unfair advantage like that, does the server end up trusting it? In most cases, the answer is yes. Now, this can be exploited using both hardware and software approaches, and it's actually a big enough problem that a lot of modern consoles try to detect hardware-based devices that do this, known as lag switches. Next. Now, race conditions. This is another example of a time and state management issue. Now remember that a lot of things are happening simultaneously in a lot of online games. There are a lot of complex interactions that are hard to see during development and testing that can pop up really, really quickly and repeatedly when millions of players are playing simultaneously. So let's take a look at the example here on the slide. Here, player 1 and player 2 are connected to the same game server. Player 1 tries to perform two actions simultaneously. Player 1 tries to give an item to player 2 and also tries to move to a different game server. Neither of these actions is going to be atomic. The various steps for the two actions could get interleaved when they're actually executed. So what are the possible outcomes here? The item could get transferred to player 2, which is what we want. The item could remain in player 1's inventory and not get transferred to player 2. Now this isn't ideal, but it's acceptable. The item could just disappear altogether. Now this is something that's going to drive up your customer service costs because people tend to get pretty upset if they start losing their in-game items. Now finally, the item could get copied so that both player 1 and player 2 end up with a copy of the item. Now this is a duping bug. People find these in online games all the time. So we have a sequence diagram on the right showing how this can actually happen in an online game. Next. Now let's talk about actual game hacking and cheating techniques now. Now, if a game client or the platform that it's running on doesn't try to make patching game clients on disk difficult, then this is probably the easiest way to change all the rules of the game. So what can an attacker do? The attacker can remove security features, for example, bypass license verification to facilitate piracy. The attacker can change the rules of the game to gain an advantage over other players. For example, the player can reduce gravity in his game client, which will only affect how his character behaves in the game. Remember, other players' actions are controlled by their game clients. Now, this gives the attacker an unfair advantage over other players. The attacker could also rebrand the game and sell it. So how do we protect against that? To detect cheating, we need to perform some server-side verification of data that's sent by the client. We especially need to perform some kind of statistical analysis to find outliers, where we see a small number of players that seem to be doing things that other players aren't doing. We also use application hardening and tamper-proofing techniques as a preventative control. And we're going to talk about that in the next section. Next. Now, if the game client performs some load time integrity checks to make on-disk patching difficult, then attackers can just patch the game client after it gets loaded into memory. Now, the impact really is the same, and the prevention techniques are similar for the most part. One prevention technique that you'll see here that's different from the previous slide involves hooking system calls. Now, modifying the game client in memory from another process requires some support from the operating system. So if we can modify the behavior of system calls that are required to modify the game client's memory, we might be able to stop in-memory patching. Of course, this is only going to stop user mode exploits. If an attacker wants to drop down to the kernel level and start writing kernel-level code, he can easily bypass this particular protection technique. Next. So, proxying traffic. Now, this is an attack vector where if it succeeds, it typically has a really high reward. It essentially allows the attacker to bypass everything that's going on in the game client and just start communicating directly with the server. Now, the attacker can read or modify any information that's being sent between the client and the server, which can give the attacker information that he's not supposed to know. For example, where all of the other players are located. It can also allow the attacker to perform actions that the game client would not let him perform. For example, maybe flying in the game as a mode of transportation. The attacker can also completely reverse engineer the client-to-server communication protocol and just create unauthorized game servers. So how do we protect against proxying traffic? Well, one common approach is to use just standard protocols like transport layer security and hard code the server certificate in the game client. Now, the idea is that the game client should really only be allowed to communicate with the expected game servers over a secure communication protocol. Now, that's fine as a protection technique, but the problem with it is that attackers can actually patch the game client to modify the server certificate and put in their own. Or they can remove the certificate verification checks altogether. So remember patching the game client on disk or in memory? Well, that can be used to bypass these checks. So what we need is application hardening and tamper-proofing techniques to protect ourselves as well. Now, another common approach is to use a proprietary cryptographic protocol, which essentially forces the attacker to reverse engineer an unknown protocol and just adds additional time that the attacker has to spend in attacking your game. Now, this is great in that it adds an additional reverse engineering step. However, it is pretty dangerous because getting cryptographic protocols right is very, very difficult. Even if you do manage to get it right, you'll still need application hardening techniques to make sure that your game client is not very easy to reverse engineer. Because if the attacker can easily reverse engineer the game client, then they'll be able to reverse engineer your communication protocol. Next. Modifying data files. So modifying data files can enable the types of attacks that we saw earlier, things like texture hacks, where you can potentially start seeing through walls. And you can make other players' textures brighter to make them stand out. To protect against this, you'll need to verify the integrity of data files in your client-side code, and then protect your code using various application hardening and tamper-proofing techniques that we're going to talk about in the next section. Next. Now, modifying system software or drivers is an advanced attack that can allow attackers to get under all of the user mode software for the game and bypass all of the security checks and controls that are in place in user mode. Now, that's where the majority of code for a game lies. Now, there are some techniques for detecting and preventing these types of attacks, but that's really an advanced topic that we don't have the time to discuss right now. Next. Now, instead of patching the game client that contains state management code, attackers can modify the actual game stack and heap contents, which represents the player's current state. So instead of modifying the code that controls the state, you can just go and modify the state yourself. Or you can modify the game's control flow using a debugger. The end result is often the same, and the prevention techniques are also similar to preventing in-memory patching. The attacker is just modifying a different part of the process's memory. Next. So attackers often end up creating bots using the techniques that we talked about so far to automate boring tasks in the game, or to gain some sorts of superhuman abilities that they normally couldn't get if they were actually playing themselves. We saw an example of aimbots that Rennie showed in the previous section. The most effective countermeasure against bots is typically just statistical analysis of the gameplay. So preventing bots is kind of difficult. It can be done in some cases, but bots, we have to keep in mind, are generally easy to discover through statistical analysis because they tend to keep doing the same thing over and over and over again, or they tend to give the player some superhuman abilities that nobody else in the game seems to have. So through statistical analysis, we can typically find these pretty easily. Next. So modifying hardware is a large class of attacks on its own, and we're not going to talk about this in detail. But we do want to mention it just for the sake of completeness. Now, if I can modify my game controller to send automated button clicks faster than any human possibly could, then I could gain an unfair advantage in the game. So again, statistical analysis and maybe some hardware controls for detecting modifications can help with these kinds of attacks. Next. So here's a quick summary of the attacks that we just discussed. Now, just a couple of most important points here are, well, there's no one attack vectors that allows you to do everything, and no one protection technique can help stop everything. So note that no security in does have a check mark in all of the rows, but it actually consists of many secure software development lifecycle activities. So there really isn't just one technique that you can use to solve all your problems. At this point, I'm going to pass it over to Rennie.
Thanks, Amit. So what I'm going to focus on now is just, Amit had mentioned a few times there that you should harden the code against tampering. So I'm going to talk about Arxan's tool a little bit, which actually does allow you to harden your code so that it can't be modified. So there's two steps for an attacker to modify something. First thing is they have to understand your code in order to be able to make a change that will gain them the effect that they're looking for. One of the techniques to prevent an attacker gaining an understanding of your code is to obfuscate or encrypt it. So encryption typically prevents on-disk understanding, so static analysis of the program, loading it into IDA Pro, and it basically forces an attacker to do a memory dump if they want to. They have to memory dump the program after it's loaded in order to get a version of the program that they can statically analyze. And then obfuscation works even after that. So even if they do a memory dump, if you obfuscate the code at the machine code level, it makes it very difficult for an attacker to follow the code of the program, and just it really slows down the rate at which they can understand the program in order to make the change. It's very effective at creating an initial barrier against the sort of amateur or hobby attackers. But of course it will not stop the professional the professional hackers, the guys who create commercial cheats for your game. And so to move to that stage, you need to go to software anti-tamper. And so software anti-tamper basically allows the code to defend itself against memory-based attacks at runtime. And you can take a number of actions against it. You can have the code self-destruct so that the attacker just can't produce a commercial hack that will actually run, because the game itself will shut down. And the other technique is that you can actually sort of do a form of runtime encryption, which allows the code to stay encrypted even at runtime, so that it basically can't be changed. It actually decrypts just as it runs. So any attempted patches to the code are overwritten by the guard, which then which basically decrypts the code. So every time the code runs, it decrypts and fixes itself. The other thing to mention, especially with online games, is using white box cryptography. I won't get too deep into this because it in itself is an entire webinar. But basically, the idea there is to hide your keys that you use for encrypting your messages that you send back to the server, so that they can't be discovered by an attacker. And that makes it very difficult to do any kind of proxy attacks or network injection, packet injection attacks. So the way that the anti-tamper works in terms of Arxand's product is it basically decodes all your instructions. It reads in your binary, decodes the instructions, and then basically if you have some code you need protected, here it's demonstrated some code inside the call graph of your overall program. You can then apply guards to that particular code so that it can't be modified. You can checksum it, you can repair it, which is a form of runtime encryption, and you can then layer these guards on top of themselves. So the guards themselves can either guard your code or themselves, and that's really where the power comes from. Because you increase the difficulty for the attacker exponentially. So a linear effort on your part is an exponential effort on the attacker's part. And, so that basically puts the calculus in your favor at that point. And so essentially you layer these network of guards and that gives you protection. When you have the binary code protection applied, here's just sort of a sample of a program that's run that has not been tampered with. And when it has been tampered with, and this is in the debug mode, and it shows that the guard has detected tampering in the code at runtime. And with that, I will hand it back to Amit just to wrap up. Hello?
Okay, sorry, I was on mute. So hopefully it's clear by now that a server authoritative architecture is not always going to be possible for online games. So we need some way to balance security with performance. So how do we do that? Well, first, we should implement some preventative controls on the client side and use binary code protection techniques to protect those controls. Keep in mind, though, that anything you implement on the client side can eventually be bypassed. Second, implement some preventative controls on the server side that don't severely impact performance. As network speeds and computational abilities improve, we'll be able to do more and more checks on the server side. Finally, implement some detective and reactive controls on the server side. Just because you can't stop all attacks in real time doesn't mean that you shouldn't take action against cheating players later. Now, doing all of this isn't easy. You do need to think about security throughout your software development lifecycle to be able to do this properly. And with that, if anybody has any questions.
Thanks, Amit. And Thank you, Rennie. I believe this has been very informative, and we are at the top of the half hour here, so I think we have time just for one question, and Amit, I'll read it out, but I think you might be able to address this one. The question is, at what point of game design or development would you introduce binary code protection?
Okay, so although you do need to think about security throughout the software development lifecycle and perform some security touch points throughout the software development lifecycle, the binary code protection techniques are typically best applied later on, right before the application goes to QA. So once you're done developing it, then you can start implementing the network of guards that Rennie had talked about, and then you can actually go ahead and test your application.
Okay, and for those that have submitted a question, we have noted it, and we will get back to you individually through email to ensure we provide you a response. Thank you, everyone, for attending our webcast. We hope you found it enjoyable and informative. Thank you.